Hello there, this is Jude Socrates. Welcome to Multivariable Calculus. This is our 22nd video, and today we are going to talk about spherical coordinates. So this will be a new way by which we can look at solids in space and a new way to integrate a triple integral. So it's going to feel a lot like that time when we talked about polar coordinates when we saw it for the first time. If you're looking through our textbook, it's at page 160. And if you flip through it, it's going to feel a lot like what we did in polar coordinates. So I'm going to show you what does it mean to be in spherical coordinates, how do you plot a point, what do some of the basic surfaces or equations look like when you graph them. We'll do a lot of pictures in GeoGebra. And the hard part is converting the volume differential, the dV. It was very easy for cylindrical coordinates because it was basically polar. So it was like RD theta, okay? And there's just an extra dz there, big deal. Not much difference. So here we're going to find out it's going to be quite different for spherical coordinates. But the good thing is that basically, even if you are not completely confident about understanding the how we derived the formula for dV, doesn't really matter. All you need to remember is the final bottom line, which is very short and very simple. Okay, so from there we're going to look at some triple integrals. And so in a minute I will join you on page 106. All right, so first of all, what do spherical coordinates look like? So instead of x, y, z, Cartesian, we're going to have three coordinates still. We're going to have a rho, a phi, and a theta. Okay, so these two don't look familiar, maybe not so much. Theta we saw in polar coordinates, and the good thing is that it actually means the same thing there as it does in spherical coordinates. Okay, so the easy part, rho. What is rho? It's a distance. All right, so it's just the distance from the point to the origin. Okay, so in this case, we got 4 plus 1 plus 4. That conveniently adds up to 9. Yeah, I rigged that. So we get square root of 9, which is just 3. One nice thing about spherical coordinates is that rho is always positive or 0. So just like in polar, if rho is 0, you are at the origin. Okay, anywhere else, your rho is strictly positive. Okay, so what about this phi? So phi is the angle made by the vector from the origin P with k, which is basically the positive z-axis. Okay, and by convention, because we have an angle between two vectors, remember way back in chapter 1, we said that the angle between two vectors is going to be from 0 to pi. Okay, so unlike theta in polar coordinates, you can go up to 2 pi or even negative. No, none of that nonsense. Phi will be between 0 and pi. Okay, so here I plotted P in Cartesian. So phi is this angle that OP makes with the positive z-axis. Okay. What about this last angle, theta? It's exactly the same thing that we did in polar coordinates. So we dropped P to the xy plane to the point Q. Okay, so there's a point Q over there. Because we have negative 2, 1, 2, it's just negative 2, 1 on the xy plane. Very simple. Okay, so our theta is the angle from the positive x-axis to that vector, as usual. So in this case, it looks like we can write it as an inverse cosine. Okay, so both of them, actually, we can write as inverse cosine, because again, we have the formula for the angle between two vectors. Okay, so you take their dot product, divide by the lengths of the two vectors. Oh, but check it out. The length of OP is just our rho. The length of K is just 1. And what happens when you dot a vector with K all that survives is the z coordinate. Okay, so shortcut would be just the z coordinate of the point divided by its length, or the length of the vector corresponding to that point. Okay, so cosine phi is 2/3. Phi is inverse cosine 2/3. Okay, which is still in the first quadrant. All right, so what about our theta? Do we have a theta? Yeah. So one way we can do it is the inverse tangent, because we have rise 1 over run -2. So our tangent is -1/2. Inverse tangent, though, takes us to the first or the fourth quadrant. Okay, so if we were just to use inverse tangent, no, we have to make a slight adjustment. Okay, so we have to add pi to it so that it takes us to the second quadrant as it should. Okay, so here are the full spherical coordinates of our point P. Our rho is 3. Our phi is inverse cosine 2/3, what we got here. Our theta is inverse tangent -1/2 plus pi. Okay, so I made a little program, sort of, in GeoGebra that allows us to play with these coordinates. Okay, let's go there. All right, and of course, this is how I made the screenshots. So here's my little program. I have the point P, the same one that we have in the example, and A is the origin, B is the vector K. So you can draw an angle by specifying 3 points, and the middle point should be the vertex. Okay, so alpha is actually our angle phi. Let's make it blink. Yeah, there you go. So there's our angle phi. By the way, if you want to label an object in your diagram, I don't think we've talked about this, you can go to settings, and let me move myself here a second. Notice how I have a caption here. Okay, so instead of using the default name for that object, you can tell it, this is what I want to see on the screen. Okay, so show label caption, and that's what you're going to see. All right, so let's hide that now. So this is the annoying thing sometimes about GeoGebra, that when you do work like that, suddenly your screen looks weird. So what you do is right click and go to standard view. There you go. And as you can see, I'm only showing the positive X and Y axes. Okay, so you can, as usual, rotate it that way. There you go. Okay, so I have also the point Q, which is down on the XY plane. And again, I make an angle between Q, the origin, and the x-axis, which is 1, 0, 0. Okay, so that is what we have for theta. Now we can play with this. We can change the coordinates, but it's a little bit old school. Okay, so if I change P, I also have to remember to change Q. Otherwise, it doesn't make sense. The z coordinate is always 0 because we're on the xy plane. So even if you change z, like what happens if it were -2? Oh, okay, so there you go. It's flipped over. So notice that theta stays the same. Can you zoom in? Yeah, but phi is now obtuse, okay, because we are below the xy plane. Okay, so maybe let's bring that back. Now, what about x and y? Yeah, we can change them to anything we want. So we can make this maybe a +3, and maybe this a +5. Okay, except again, it's old school, so I need to change this manually also to 3 and 5. So that's the projection on the xy plane. And let's see, did it work? Oh yeah, there you go. Okay, so so P is a lot further now from the origin. Okay, and phi is that angle, Q is the projection, so theta is over here. Okay, So yeah, can we do the arithmetic in our head? 9 and 25, 34, and 4, 38. So square root of 8, 38 is our distance, our row. What is our phi? So we said it's z, the z coordinate is still 2 over the distance, 2 over square root of 38. So we have inverse cosine 2 over square root of 38. And what is our q? I mean our theta corresponding to q. So yeah, we have y over x, right? So 5/3 is our tangent of theta. So we have inverse tangent of 5/3. Okay, so yeah, I will include this in our GeoGebra file section. You can play with it. There's really not much to play with. There's another program that's a lot more fun, and we'll see it. All right, so let's talk about conversion formulas. We said that rho is the distance from the origin, so it's just square root of x squared plus y squared plus z squared. Cosine phi, we use the standard formula of the cosine of the angle between two vectors. So we said we just extract the z coordinate and divide by the distance that we just obtained over there. And so phi is the inverse cosine of this sort of ugly looking thing. You can just keep it like this if you like. Tangent to theta as usual is y over x, but you have to make an adjustment in case we're in quadrant 2 or 3, okay, because inverse tangent takes us from to quadrant 1 or quadrant 2. All right, so if you're in quadrant 3, both x and y are negative, you just have to add pi so that you taken to quadrant 3 instead of quadrant 1. Okay, so we're going to need this a little later. So we will also think of theta in terms of our polar coordinates from before. So cosine theta is x over the r. Okay, so as usual, it's square root of x squared plus y squared. Similarly for sine theta. Okay, so from here we can now let's think about going backwards. Okay, so if you're given spherical coordinates, how would you find its Cartesian coordinates? Okay, so z is easy. Okay, so we see over here that z over rho is cosine phi. So therefore z is just rho cosine of phi. Okay, now let's do some fancy trigonometry. So because we have cosine phi, we also have sine of phi. So sine squared phi, 1 minus cosine squared. So if you do that, common denominator, rho squared is this. The z squared cancels. So you have x squared plus y squared over rho squared. That's r squared over rho squared. Okay? So if we agree that our r is going to be positive, then sine of phi will be r over rho. Okay. We also said actually that rho is between 0 and pi. Okay. So therefore, the sine of an angle between 0 and pi is always positive. Okay. So this formula actually forces the r to always be positive as well. Okay, r will be almost like a temporary variable for us. Okay, because what we really need are x and y. Okay, so from polar coordinates, x is r cosine and y is r sine. Okay, so we have these two formulas for x and y, and what you really have to remember, especially when we go back to taking tests in person, you need to remember the formulas for x, for y, and for z. All right, so in part A, we took a Cartesian, point in Cartesian coordinates, plotted it, and then described how do you get rho, phi, and theta. Okay, so this time, what if you're already given rho, phi, and theta in that order? Okay. So, of course, the fastest way to plot this in GeoGebra is to use the conversion formula. Okay, so everyone knows these two famous angles. So this will be the point in Cartesian coordinates. Okay. Now you can be really super lazy and just type this in GeoGebra, and it will spit this out for you, approximately, of course. Okay, what if you're doing this, I'm going to put air quotes, by hand, okay? What if we didn't have GeoGebra, okay? How would you draw this point in space, okay? So this is how I like to think about it. Start with the angle theta, pi over 3, okay? So that's this angle over here. It's on the xy plane, okay? So from here, we can create a plane which is going straight up and down, okay, containing that vector, okay. It's almost like a door, a swinging door, actually, okay. When the door is closed, that's your theta equals 0, okay. And if it swings in a let's assume the door swings in a counterclockwise direction, okay. As the door swings, your theta increases, okay, until maybe the door is as wide as it can be. Maybe that would be your pi, okay? Or if you're on a corner, the door will only swing up to pi over 2. Okay, so now we have this door. We can measure the angle phi, okay, which is pi over 6, okay? So measure that angle from the vertical, the z-axis, and then along that vector, mark off our rho, which is 4. 1, 2, 3, and 4. Okay? So that is where your final point is going to be. Okay, time for us to draw more interesting pictures, namely surfaces in spherical coordinates. Okay? So the easiest way to create a surface in spherical coordinates is to make an equation. Let's say set one of the coordinates to a constant. Okay? We saw something like that already in Cartesian coordinates when we set an expression in 3 variables equal to a constant. Okay? In this case, I didn't make y very complicated. We can solve for y. Ooh, check it out. We get a paraboloid, an elliptic paraboloid. Okay, so that's a surface in space. All right, so what happens if we set one of the spherical coordinates to a constant? Let's start with theta. Okay, if we fix theta to pi over 3, remember that swinging door? Okay, so we set the angle that door makes with the door frame equal to pi over 3. All right, that's what we have over there. Same diagram because I'm using the same angle. Okay, so remember how we drew the point P. Okay, so we drew the plane, the door frame, the door, not the door frame. Okay, and then we said, okay, now you can make an angle phi from 0 to pi. Okay, so those are these arcs over here. Okay, because I obviously used surface to create this diagram. Okay, rho can be any positive number, so that's these radial traces that we see produced by surface. Okay, so that's the surface command for that equation. Okay, notice that, yeah, I told you something about being lazy, right? So these are the conversion formulas for x, y, and z. I'm using them in my surface command. Okay, so rho can be any positive number, but you know, I'm not sure if it's possible to represent infinity in GeoGebra. I'd rather not mess with it. Okay, but phi though, phi can be any angle from 0 to pi. So that's why I have this parameter for phi. Okay, and of course our theta is constant at pi over 3. So that's in our x and our y. Okay, so of course if you increase 5 to any number, any positive number that you want, this half disk is going to get bigger and bigger and bigger. Okay, so as rho goes to infinity, it's not so much a half disk anymore. It's really a half plane, okay, that we get in spherical coordinates. All right, so of course it's true in general. If you make theta be a constant, you'll get a half plane. It's going to be perpendicular to the xy plane, and it will contain the terminal side of the angle that alpha makes with the xy plane. Okay, let's have a ball. Here is the equation phi equals 4. I'm sorry, no, that's not phi. Rho equals 4. Okay? So we want to find all the points in Cartesian space where rho is 4, phi can be anything, theta can be anything. Oh, did I say anything? Phi can be any angle between 0 and pi. Theta, let's just say that it's going to go from 0 to 2 pi. Full circle. Is there any need to go beyond that? No, because of our conversion formulas. Cosine theta and sine theta will take us back where we started. Okay. So, of course, that obviously produces a sphere, okay, because rho is constant at 4. Rho is our distance from the origin. Whoops, I have a typo over there. Of course, in the diagram, I did have that as 4. Okay, I need to correct that. Page 163. Okay, that should also be a 4. And we get a sphere of constant radius 4. All right, so of course this is true in general. If rho is constant at 4, we can square both sides and get, ooh, that looks familiar. That's the equation of a sphere of radius 4. And of course, if you change 4 to rho, you'll get rho squared. It's the sphere of radius 4, of radius rho. So what if we now fix phi, the angle of phi, to be a constant? Okay, pi over 6, let's say. So we're looking for all the points, rho, pi over 6, theta. Okay, rho can be any positive number. Theta will be anything from 0 to 2 pi. And again, that takes us full circle. Okay, we get a cone. Okay, a cone that makes an angle of pi over 6 with the positive z-axis. Okay, so again, we can use surface to trace that curve. And any typos here? No, it's actually correct. So I let my rho go from 0 to 5, and our theta will go from 0 to 2 pi. Our phi is constant at pi over 6. Okay, of course, sine pi over 6 is 1/2. We could have just put that very easy. Okay, now what is going to happen if we have a different value for phi? Okay, so how about 2 pi over 3? Okay, so this time the angle is obtuse, and so the z-coordinates that we get are going to be negative, okay, because cosine of 2 pi over 3 is going to be negative 1/2, okay? So the z-coordinate is going to be a negative number. So we have an upside down cone. Don't put any ice cream on it or you're going to cry because you lost it. Okay, there's something missing. What if your phi were exactly in the middle at pi over 2? Can you visualize it? Are we still going to get a cone? Is it still a cone? Let's see what's going to happen. Boom! No, of course not. It's not a cone anymore. It's the xy plane, okay? Because our phi is pi over 2. Those are on the points on the xy plane, because what is cosine of pi over 2? We just get 0, okay? So the z-coordinate is always going to be 0. There are two degenerate cases, okay? When theta is 0, it's the half line, which is pointing in the positive z-axis, so it's not a surface, okay? And if phi is pi, you get the negative z-axis, okay? So we're not going to use those to create our surfaces. All right, so I hope you like these pictures. They show how basically the three kinds of surfaces that we saw just now interact with each other, intersect with each other. And they also give us a different way, 6 different ways basically, to plot a point in spherical coordinates. Okay, so you can think about the ball or the sphere, where all the points are a distance 4 from the origin, and then you cut that with a cone. Okay, our pi over 6. How do they intersect? In a circle. Okay, so now which point on the circle do we want? The point that makes an angle of pi over 3 with a positive x-axis. So we now use the plane theta equals pi over 3 to get that single point. Okay, and we can see that up there as well. Okay, now we produced a cone just a minute ago, but we also saw cones back in chapter 1. Okay, and they were elliptic cones in general. All right, and because we have z squared over c squared, they're actually double cones. Okay, so yeah, I mentioned that one of the parts of the cone is called a nappe, N-A-P-P-E of the cone. In spherical coordinates, we're not going to see cones with 2 nappes, only 1 nappe. Okay, so basically we are going to look at ice cream cones in a little bit. All right, so we're going to agree that we only use the plus or the minus, okay, because we did say that you could have a cone which is upside down. Okay, because we want to be in spherical coordinates and we don't want anything ugly inside our radical, we want it to simplify nicely. Okay, so we're going to require the cone to be circular, not just elliptical. So therefore, A and B should be the same. And so we can take A outside of the square root. And guess what? We saw that before. That is the R in polar coordinates. Okay. So Z is rho cosine phi. Let's assume we have plus C over 8 times R. So we can isolate cosine phi, bring the rho over. But wait a minute, we saw this also earlier, and we said that this is our sine of phi. Okay, so now we have cosine phi and sine phi. Oh, wait a minute, if we put them together, sine over cosine, we get tangent. Aha, but C over A will flip over to the other side, and we'll get A over C. Okay, so therefore we get an equation. Phi is inverse tangent of A over C. And well, if you choose the sign of A or C to be negative, okay, only one of them, okay, then you can create an upside down cone, okay, where the tangent will be negative, but again, you have to make a slight adjustment, okay, because phi is between 0 and pi, and inverse tangent takes us from minus pi over 2 to pi over 2. So if you want to play with the negative value for A or C, I don't recommend that actually. You will have to add pi when we set up our integrals later on. All right, so here's an example. Again, we only want 1 nappe of the cone, so I'm choosing the positive nappe. Z over 4 is radical x squared plus y squared over 3. So in our standard form, this 4 is your C, this 3 is your A. Okay, so according to the formula, phi is tangent inverse of 3/4. Okay, so that is the graph of this cone in spherical coordinates. We're going to use this when we do our triple integrals because we're going to probably have a trig expression involving phi. Definitely sine phi will show up. But what if you also need cosine phi or tangent phi? Okay, so we will find those values as usual by drawing a triangle. Opposite is 3, adjacent is 4. Everyone should know what the hypotenuse is. That should be a 5. Okay, so even though 5 does not appear in that equation. So that gives us cosine 4 over 5, sine 3 over 5. All right, so we're going to put these surfaces together in order to create solids, right? We actually already know one of those solids because a sphere almost looks like a solid ball, okay? So when you're looking at a picture, let's say of a bowling ball, and you're not sure what it is, it might look just like a balloon, okay? If it were, bright red or something, you might think, oh, it's a balloon. Oh, actually, it's a bowling ball, okay? Those are very different things, right? A bowling ball is solid, okay? Maybe except for the 3 holes. So, if you prefer a billiard ball, so that is also solid, as opposed to a balloon, okay? A balloon is mostly air, right? You have this thin rubber on the surface, okay? Inside, it's all air, okay? So what we want now is to create solids using our spherical surfaces, okay? So let's start with a sphere. How do you turn it to a solid ball? So you consider all the points which are on the sphere, but also inside the sphere, okay? So how do you make that happen? You use an inequality. So the distance from the origin should be at most 4. Okay, so this is how we would write it out in set builder notation. We want all the points rho, phi, theta in spherical coordinates. So that rho is between 0 and 4, phi is between 0 and pi, theta is between 0 and 2 pi. Okay, so if you only have the number 4 over there, you get a sphere instead of a solid ball. Okay, so remember back in the start of chapter 3, we started with creating triple integrals over solid bricks. Okay, so remember it was A, B, C, D, R, S. Okay, so we can use the same notation here to create a solid ball. Rho from 0 to 4, so that's the closed interval 0 to 4. And then we have 0 to pi, and then 0 to 2 pi. So you put the times symbols in between them to represent a Cartesian product to create what we call a spherical brick. It sounds weird, right? Bricks aren't round or spherical, okay? But we'll use the same term as we did in the beginning of chapter 3. All right, so this is the general notation for a spherical brick. Rho will go from A to B, phi from alpha to beta, and theta from mu to nu. Okay, so yeah, we're kind of running out of Greek names. So I think we've seen the word, the letter mu before. Not really sure. You see it a lot in physics. And same thing with nu. So these are chronologically next to each other in the Greek alphabet. Basically the letters M as in Montana and N as in Nebraska. Okay, so that is the general notation for a spherical brick. Okay, so we can take our solid ball and we can carve out portions of it. Okay, I always think about cutting up a melon or something when I see these pictures. Okay, so yeah, you can take the upper half of the ball, or you can take, what would this be? This is the positive x-axis, so this is the right half of the ball, and you can take the portion which is in the first octant. Okay, we'll see a lot of problems where we say the portion of the solid which is found in the first octant, okay, so that all the coordinates are positive. How will we describe this using spherical bricks? Well, rho will still go from 0 to 4 for all of them, Okay, it's the phi and the theta that are going to change. Okay, you want the upper half. So phi is going to go from 0 on the z-axis down to pi over 2. Okay, so remember that the xy plane has equation phi equals pi over 2. Theta can go around full circle. So theta from 0 to 2 pi. Okay, it's slightly different for the right half of the solid ball. Okay, let's check it out. Phi now has to go from 0 all the way down to pi, because we want to end up in the negative z-axis. Okay, what about theta? You want to start on the x-axis, go around counterclockwise until you're in the negative x-axis. That's also 0 to pi. Okay, so check it out. I want to show you something really weird. Okay, this is 0 to pi, 0 to pi. Okay, so yeah, if you might think that, oh, pi plus pi, 2 pi. Oh, but wait a minute, I already have 2 pi over here, but I have a little bit more over here. Okay, that should be a little strange. But remember, that looks like a product, right? So the right way to think about it is pi times pi. You get pi squared. Okay? 2 pi times pi over 2, you still get pi squared. Okay? This is a very, very rough hand-waving thing. Okay? Don't take it too seriously. So it's only fair that, given that their products are the same, you get the same portion, the same amount of that solid. Okay, what if you only want the portion in the first octant? Okay, so phi will go from 0 to pi over 2, the xy plane once again. But now theta will rotate only from 0 up to pi over 2. Okay, so therefore we get this portion. Let's see, what happens if you multiply these? Pi squared over 4. We only got pi squared, right? So is this a quarter of these? Oh, yeah. Check it out again. Think of it as a melon. Cut it this way, and again cut it this way. Okay, so that produces a quarter of that melon. Speaking of melons, okay, so what if you scoop out a portion, where the seeds are? Because, we don't eat the seeds. Okay, so our sphere has radius 4. Okay, what if you scoop out? Okay, so I kind of tilted the view so that we're actually looking from below the xy plane here. So I scooped out the upper half of the ball of radius 2. Okay, so these are the same diagrams, exactly the same diagrams as we have up there, except I scooped out that half ball. Okay, so they're all the same. Oh, look, I still have those products over here. They're exactly the same, cut and paste, literally. Okay, except now 0 to 4 is replaced by 2 to 4. Okay, so this will become important when we set up our triple integrals. Okay, so yeah, fruits are a little bit too healthy for me. So how about some ice cream? Anyone for ice cream? We can create a solid ice cream cone where the boundary above is a sphere, okay? And the boundary below is a cone, okay? So we will put together those two surfaces and we're going to get something like this, okay? So we saw this cone a few minutes ago, okay? So we have our phi equals inverse tangent 3/4, same formula, okay? So how big should the cone be? You can make your row any radius that you want, okay? So here is rho equal to 6, okay? Now, remember when we talked about polar rectangles, and we said if you're going to do a double integral in polar, you have to make sure it's appropriate, okay? So you shoot out rays from the origin, okay, going from 1 theta to another theta. Okay? The test for spherical bricks is very similar. You stand at the origin, and then you shoot arrows through the solid in all directions. Okay? Until, oh wait, you're now missing the target. You are missing solid entirely. Okay? So you start up here in the positive z-axis. Okay? That's phi equals 0. And then you can lower your angle, or I should say increase your angle until you're at this angle, and then the solid stops. Okay? But you stay inside the solid until you exit at rho equals 6. Okay? Can you go all around the solid? Yeah. You can go from theta equals 0 all the way around until you get back where you started to 0 equals 2 pi. Okay, so I'm going to scroll a little bit, a little more. There we go. So that is our spherical brick. Rho from 0 to 6, phi from 0 to inverse tangent 3/4, theta going from 0 all around to 2 pi. That's your spherical scan test. All right, so I'm going to end the video here because we're already at 41 minutes and you're probably exhausted. I know I am. So just like what we did for polar coordinates, we introduced it first. What we still have to do for spherical coordinates, as I mentioned, is what do you do about your dv? Okay, how are we going to change dv for spherical coordinates? Okay, and then how do you set up and compute the integral? Okay, so I will sign off at this point. I hope you enjoyed this video. I'll see you next time when we complete our tour of spherical coordinates. Bye!